In this video, I want to explain what an inductor is. But first, let's start with the properties of a piece of wire. I'm going to induce a current to flow in this wire that I will call I. An interesting thing happens. A magnetic field is produced around this wire. And I'll denote this magnetic field by the symbol B. If I were to put a compass really close to this wire, the needle would deflect due to the magnetic field of the wire. As I move the compass further from the wire, the effect of the magnetic field becomes less. Now this magnetic field stores energy. If I increase the current flowing in the wire, the magnetic field becomes more intense. It stores more energy. If I stop the current, the magnetic field goes away. It stops. If I change the direction of the current, for example, if I run the current in this direction, instead, the magnetic field will reverse and it will go in this direction. Let me change the color of this current arrow. So another interesting thing happens. Let's take another piece of wire and I'll bring in a second wire very close to this first wire, and I will put an ammeter in this second wire, and we'll call that A for ammeter. Now if I induce a current change into this top wire, I'll call it delta I. An interesting thing happens to the wire below. As I change the current, the magnetic field in the top wire changes, and this changing magnetic field induces a current in the bottom wire. So I will get an induced current here. So if I have a little spike of current, the key thing is the current must be changing. So if I have a spike of current in the top wire, again this is time, and we'll say this is, for example, current. I have a little spike of current, and that induces a spike of current in the second wire, which the ammeter, I may see that it's just a little blip. This property is the basis for a transformer, and we'll talk more about transformers in the future. Let's take advantage of these properties and make an inductor. We can do that by taking a wire and producing a coil. And this, as we run current into this coil, it'll produce a magnetic field. And what will happen, because of the coil, the magnetic field inside of this coil region will become stronger. So let's draw the magnetic field. And this strong magnetic field will increase the inductance properties of this wire. The electronic symbol for the inductor is just a coil. It has a terminal at the top, a terminal at the bottom, and we denote inductance by the letter L. Let's compare an inductor to a capacitor. We know that a capacitor stores energy in an electric field, we'll call E. And we know that an inductor also stores energy, but in a magnetic field. To create this electric field in the capacitor, I must apply a voltage across the plates. To create the energy field in the inductor, I don't apply voltage. Instead, I run a current through the inductor, I. So the role of voltage and current is reversed between the capacitor and the inductor. To create energy in the capacitor, I apply voltage. To create the energy in the inductor, I apply current. You've probably heard the word electromagnetic. The electro part of that word comes from the capacitor, and the magnetic part in electromagnetic comes from the inductor. Let me erase this. Let's continue with our comparison of inductors and capacitors. We know from a previous video that a capacitor will resist change in voltage, but an inductor will resist change in current. So again, the role of voltage and current has reversed between the inductor and the capacitor. For example, if I run a current into a capacitor, I call this I know that the voltage across the capacitor will ramp up. So this is the voltage. However, if I apply a voltage across the inductor, I'll call V, the current will ramp up. Call this I. So again, the role of current and voltage is reversed between the inductor and the capacitor. Now let's compare the parallel and series properties of capacitors and inductors. We know from a previous video, if we have two capacitors connected in parallel, that to compute the equivalent capacitor, we just add the two capacitors together. However, with an inductor, if we have two inductors in parallel, to calculate the equivalent inductor of the two, is the product of the two inductors divided by the sum of the two inductors. But in series capacitors, the equivalent capacitor is a product over the sum. But series inductors, to get the equivalent of the series inductor, you add the two inductors together. So again, the roles are reversed between the capacitor and the inductor. So in one way, if you know the characteristics of a capacitor, you can infer a lot of the characteristics of the inductor by just knowing that voltage and current is often reversed, and that the parallel and series equivalents are also reversed.